Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Today is a time of enormous opportunity. Many different processes are coming together, converging to call for changes in the way that we use energy. And fortunately, we have a huge opportunity for change. What this slide shows is the amount of energy that we use, which is about 39%, and the amount of energy that we waste. So we waste the vast majority of the energy that we consume. And this waste isn't just people who left their lights on or fell asleep watching television. That's even more waste that isn't included in here. Most of this waste actually comes as a function of the fundamental physical laws that govern burning and heat engines. So this is an absolutely wonderful graph, which is made by Lawrence Livermore Laboratories, and it summarizes all the energy use in the United States. So at the far left is the graph I just showed you, which is the overall used to wasted fraction. Below it is who is wasteful. And if you look at transport, you can see transport is terrible. Transport wastes about 80% of the energy, whereas industry is quite good. They are up at around 80%, and residences are okay, and electric power isn't very good. The waste that you see in transport and electric power is a fundamental feature of the basic science of burning. The only way to change this is to change fundamentally the technology that we use. So I could give a 5-hour lecture on this graph. It's a great thing to meditate on quietly and in private. What you have at the very far left here is the different energy sources. So we have solar, petroleum, coal, natural gas, and then as you go across the graph from left to right, you go from the sources to the uses. And there's also a part that goes off into the waste. And that's where this waste fraction comes from. The upper gray area is the wasted part, and the lower part is what we actually use. So if you want to know in detail where your energy comes and goes, I strongly recommend this graph. A brief summary here of what the major areas are. Petroleum is about 1/3, natural gas is about 1/3, coal is about 20%, nuclear is a little under 10%, and renewables account for the rest. So if you wonder where the energy goes, transport takes 1/3. Electric power is already a huge fraction, about 40%. Commercial and residential are only 10%, and industrial is about 20%. And if you look at those connections across the graph, basically petroleum goes into transport and transport uses petroleum. That's most of what we do with oil. Natural gas is evenly distributed. Coal all goes into generating electricity, basically, except for those couple people who are now powering their trucks with coal. But basically, it's just about power. Renewables are spread a little bit, and nuclear is basically 100% power, except for the Navy. So, as with so many things, the United States are not uniform. If you look at energy use per capita, it's very different spread across the United States. There is a factor of 5 difference in energy consumption between the lowest state, which is Rhode Island, and the highest state, which is Wyoming. And so you can see where you live has a very strong effect on what energy use is. So this is an example where local matters. So how did we get here? How did we get in this state? Well, this is a graph of historical energy use, starting roughly at the founding of Harvard and then moving forward. And you can see that early on, most of the energy came from wood. And then there was a transition where people began to mine coal. And then you can see energy use is just taking off wildly. So with time, we just use more and more and more. Then we hit a peak, and it actually went down. And that's the world financial crisis that you're seeing there. So another way to look at it is to look at each individual source. So now you can't see the total, but you can see what does each particular part. And you can see that wood rises and then it falls a little bit. Coal rises. During this era, coal is clearly dominant. So we had an age of wood, we had an age of coal, and then we entered a diversified era where we actually use many different sources. And I think that that's going to continue well into the future. There is not going to be one energy source. We're going to spread over many of them. And you can see right now is the dominant source of petroleum, but that's basically going into autos. Now, if you look at the percentage that goes into each total, you can see it was all about wood, then it was all about coal, and now you can see the spread over all of them. Again, petroleum dominates, natural gas and coal are roughly equal, nuclear has been rising and is now flat, and renewables are hovering down here so far. So you ask, can we change? Well, for one thing, we already have. Wood is no longer the dominant power source. Whale oil is no longer important. Many revolutions have already happened. So having another one is not unprecedented. It's in fact highly predictable. A second question is, well, can we afford it? Is it going to cost too much? So one thing to do is look at what's happened recently. So this is a graph which shows the energy per GDP. So the green line is the energy per GDP, and you can see it's been falling since about 1970. So that means that the economy is growing, but the amount of energy being used per dollar has been shrinking. So shrinking energy use need not shrink the economy. And even the energy use per capita reached a peak around 1970 and has been slowly going down. So already we're naturally changing our energy consumption to use less. So one obvious point is passive is good. There are ways in which we don't have to consume any energy. And so one thing is to improve insulation. So this is a picture of one of the first buildings ever built in North America. It's an early mission building, and you can see this very, very thick wall which provides good insulation. It keeps the heat outside and the cold inside. And this is a new high-tech window. It has triple pane. It has all these fancy chambers. It's filled with inert gas. It's basically the modern version of this wall, except you can see through it. So this keeps energy in. A second method is illustrated in this Greek village. The idea is as sun comes in, it naturally heats things up. And if you've ever sat on a black car seat, it's really, really hot. It's less hot if it's white because some of the energy reflects off. So if we just changed our roofs from black to white, we would actually have a lot less heating and cooling that we'd have to do. This is a picture from Israel of solar water heating on a roof. So now we're doing double duty. You're having the heat not get to the roof where it makes the building uncomfortable, and you're taking it away to provide light for showers. But it's not just high tech in the developed world. This is a really nice project from the developing world. It's a 2-liter soda bottle filled with water. And it functions as a 40 to 60 watt light bulb. So it's completely passive. It brings the solar energy in through a tin roof and provides very nice light. And this is the cutting edge of about 3000 BC. It's a refrigerator that's based on the evaporation of water. So it's a way of keeping food cool without using any power at all. So one fabulous strategy is not to consume any energy because you don't need it. And these are various passive ways of doing that. Another option is to change the way that we actually use energy. And there are two major options. There's the evolution option and the revolution option. And here's an illustration of them. The evolution option is illustrated on the left. It's looking at the energy consumed by cars. And you can see that the miles per vehicle skyrocketed. We drive a lot more. But the fuel consumption per vehicle has gone way down. And that's because the miles per gallon, which went down a little bit initially from the 40s to the 60s, has then been rising steadily. So cars now aren't worse than they were in the 1960s. They have cup holders, and they can play MP3 music and do other fabulous things, and they use way less energy. So this is an example of lifestyle enhancement being accompanied by a big reduction in energy. But this was a slow, gradual process. There are also sudden processes. This is an old-style charger. So when you plugged in your cell phone or your camera or anything else that charged, you used to plug these things in the wall. This is a big, heavy object. It used to have copper wire in coils inside. It wasn't very efficient. This is the new style charger. You can plug it in anywhere in the world. The kind on the left only works in a particular country, for example. The one on the right will work anywhere in the world. It's small, light, cheap, and energy efficient. It's a win on every front. These are the things that I'm looking for. What things can we do technologically that use less energy and make people happier? So this is one example that I think everyone can embrace. So what I'm basically going to advocate is the all-electric revolution. So I'm going to argue that what we want to do is switch our energy consumption from burning fossil fuels to a completely electrically based system where that electricity is generated by renewables. So this is a transition in how we get our energy and a transition in how we use our energy. And that's what I'm going to talk about now. So why do we want to make these changes? Well, one reason is national security. Countries that export fossil fuels use that as a source of national power. It creates instability in places like Europe and the Middle East. If we were less dependent, not only the United States, but the world, on fossil fuels, that would allow us to be a more stable and secure place. A second is balance of payments. When we pay to import fossil fuels, that money is going away from the US, often to places with regimes of which we are not entirely fond. Another issue is the environment. Acid rain, for example, is a well-known problem. It causes a lot of issues in water supplies. It can damage buildings. There are a number of other problems associated with it. We can eliminate that by changing how we use fuel. Then there's climate change, which is probably the one people talk about most. People are very concerned with increases in CO2 levels and increases in temperature, increases in instability in climate of storms and hurricanes and snow. And so people are very concerned on a global level, on a local level, about climate and what we can do. And the final concern is health. And I mention that because people often talk about it less, but in many ways it's the largest driver in the developing world. And ultimately it's the developing world that's going to determine what happens. So this is a discussion of air quality and health. You have a picture of Beijing on the left. That's smog. You simply cannot see. The pollution is awful. You may remember the Beijing Olympics. They were very concerned about having athletes breathe the air, particularly in the marathon. And it's not just China. India is even worse. New Delhi is on the right. And to understand what our opportunities are, you can look at the different emission sources. So I've made a graph of pollutants in order here. So this is in order of fuel combustion, which is basically power plants. So sulfur dioxide, which is the cause of acid rain, comes from power plants. They produce less of the other pollutants. If we order them over here by mobile sources, so this is transport cars, carbon monoxide is a huge source from there, and you can see it going down. If we use electric cars, we get rid of the mobile sources, and if we generate electricity from renewables, we get rid of the fuel combustion sources. So we could have enormous improvements by making this transition to electric. And the US has already made huge progress. This is what we have done in 30 years. The reduction in lead has been almost 90%. Acid rain has improved a lot, carbon monoxide has improved a lot. Even evolution can make a huge difference, and we have a lot of opportunities to go even further. So if I can have one slide to summarize my major point, burning is bad. When we consume fossil fuels, it creates a lot of problems. One is this fundamental Carnot efficiency. The efficiency of the system depends on the temperature of the engine and the temperature you dump outside, which is usually room temperature. And you can't do better than that no matter how good your engineering is. So you are bound to waste enormous amounts of energy, roughly 50%. As I talked about on the previous slide, are a problem. Carbon, which is what causes a lot of climate change, is a problem. Heat dumping, which I didn't mention, you have to have some way of cooling these things, and that does heating in nearby rivers and lakes, which can change the ecosystem substantially. Then there are issues associated with extraction. There are oil wells and issues like Deepwater Horizons. There are mining accidents. There are problems in Santa Barbara right now. So getting the fossil fuels out is a problem, and then there are additional issues in transporting them. The Exxon Valdez was a transport accident. There are pipeline issues. So extracting fossil fuels to burn them has enormous amounts of bad consequences. So going all electric allows us to get away from that if we convert our power sources to renewables like wind and solar. So what does US electricity look like now? This is how we use it at present. So there's a large category here, which is cooking, refrigeration, sort of a general catch-all is about a third. Space cooling, which is air conditioners, are 21%. That's a large category. Lighting is 14% and likely to go down rapidly as we change to LEDs. And this is a particularly bad one most people don't know about. Color television set-up boxes and the DVRs attached to them use on average more energy than your refrigerator. So this is a big sort of hidden problem that people aren't aware of, but it's also an opportunity. And it highlights the challenges. People know how to reduce that power by 95%, but it means that if you turn on your box, you have to wait 30 seconds. And most people don't want to wait 30 seconds. So a technological opportunity is how to save that 95% power without waiting 30 seconds. So here's a map of electricity price, which affects how we use it. And again, there's an enormous variation in price. In Hawaii, it's 34 cents per kilowatt hour. In Louisiana, it's only 7. So that's almost a factor of 5 difference in price. And if you look at the map I did before of energy use per capita down here, you can see that places with high electricity prices also have less overall energy use. And I think there's probably a relationship there. Cost affects what people do with energy. So one way to change energy use is to change cost. So this is a look at just electrical power. What I showed you before was all the energy in the US. This is just electrical energy. And again, it's divided into different categories, which have been shifting. So you see the trend: overall increase, financial crash in 2008, which had things go down. And you can see that coal rose and then it fell. Natural gas has been expanding because of new techniques of extracting power. So this is now a graph of each individual source. Coal, you can see, has had the rise and fall. You can see the enormous increase in natural gas as more sources have become available, whereas nuclear has gone more or less flat. So this is renewables only. They were small enough on the other graph that it was hard to see. If you look at the electric power generation, you can see there was a big growth in hydropower as people built more dams. And then it's been flat since 1965. There's been no significant increase in hydro. And then very recently, there's been a big increase in renewables with wind, et cetera. So because our power use has been increasing, that constant amount of hydroelectric power has been shrinking in fractions. In 1945, we used to generate roughly a third of our power from hydro, and now it's down to about 5%. So again, we've already had revolutions. It's happening whether we like it or not. This is our opportunity to guide it and make it do what we want. So here I've blown up an even tinier slice. This is the non-hydro renewables. And you can see the huge growth in wind here, which is taken off, and solar is just beginning to rise. And it could take off following wind in the next couple of years. So a huge factor in determining whether people want to do something is costs. And the hard thing about renewables is the cost is very different. If you're consuming fossil fuels, if you have a gas heater, for example, then you buy natural gas and you pay for it as you use it. In contrast, if you buy a solar panel for your roof, you pay for it and you have it for 30 years. So you pay up front, say $10,000, and then whether you make money on it depends on how much electricity you don't buy for the next 30 years. And the problem with that is to figure out whether it's a good economic decision, you have to know what electricity is going to be for the next 30 years. And if you know that, you don't need to worry about saving money on your roof because you already have a much better way of seeing into the future. So if you look at prices of fossil fuels, here's a graph of oil prices. The gray is real dollars, and then the red is inflation-adjusted dollars. You can see there was a big peak with the oil crisis. It went down again, and then it was going up. So it's very hard to predict that. Who would predict the big Middle East problems that gave rise to that oil crisis? Similarly, the coal price has been falling and then rising, and natural gas is up and down and up and down. So it's very hard to predict. The consumer electricity prices overall have been falling. So it's really hard to estimate, should you put a solar panel on your roof? And of course, it depends on where you live. In Hawaii, it's pretty much always a good decision. In Louisiana, it's probably not. And another important thing to think about in the next 30 years is not just the cost of the fossil fuels you would replace, it's also the other associated costs. There's the carbon cost, and I took the Obama administration's estimated carbon cost to make this graph. So this is a graph from the Energy Information Agency of the price in cents per kilowatt hour of different sources of electric power. And then I added on the carbon cost for natural gas and coal. So this magenta line is the carbon cost of natural gas added in. And you can see then wind and geothermal and hydro are all roughly comparable. But things like offshore wind are still way above. Coal was more expensive to begin with, and its carbon is more expensive. It's more expensive than any of the renewables. But we don't really know what carbon policy is going to be. Is there going to be a tax? Are they going to include other pollutants? We have no idea. So the costs are very difficult here to estimate. But it's important to understand that renewables are a cost you pay once up front, which is then amortized over 30 years. Whereas gas and oil, you just keep consuming each time, and then you add up how much you're using. So energy from renewables. Could we do it? I say we should have a revolution, but if you can't do it, there's no point. So is there enough sun to make this possible? Because it turns out renewables basically come from the sun. So a useful way to think about this is to think about energy or power per meter squared. Because as the sun comes down, it delivers energy, and so you can look at how much energy we have to use. So to compare how much we need, I made a calculation of how much power the US uses. So the US total energy comes to 0.34 watts per meter squared. So that's how much energy you'd have to harvest in order to provide the entire the entire energy for the US. The electricity is only 0.045. So if you look at the renewable sources, if you look at hydro, can't do it. And I'll give you a discussion of why that's true. There just is not enough hydro energy. On the other hand, there's plenty of wind and plenty of solar. So it is going to be possible to do that. But that depends on population density. This map on the upper left is population density. Green and yellow are lower, so Canada is low, the US is pretty low. Europe is higher, and many European countries will be challenged for that. And India, you'll note, has a very high population density. So different countries have different challenges, but fortunately most countries use much less energy than the US. So they can potentially meet their needs with numbers that are lower than the numbers that I gave here. So first, hydropower. Everybody loves hydropower. It makes cute graphics, they're nice dams, they're good for kayakers. Basically what happens is the sun shines, it evaporates the water, which does work to lift the water. So in the way that if you want to lift a bucket of water, you have to use energy. In the case of the sun, the heat of the sun does the energy to lift the water. The rain then falls naturally back down, and that's what's captured in hydro energy. The water is put behind a dam, which is nice because it stores the energy. You have a rainstorm, that's a big delivery of water, but you don't have to use it right away. You can store it by accumulating it behind the dam. In dams, they don't usually flow over the top. Little dams do, and it's sort of nice to look at, but it's not very efficient. What big dams do is use the pressure. And you know, if you go into a swimming pool and you dive down, your ears start to hurt as you go lower and lower. That's because the water pressure is increasing. So as you make your dam higher and higher, you get more pressure. And that bigger pressure pushes harder on a generator. So the higher your dam, the more power you can generate. So the important point here is that the increase in height of the dam gives you more energy. So if you want to generate power, you want to make a big dam. But if you figure out how much water falls on the United States and you put it all behind 100-meter dams, it just isn't enough. So hydropower is great, but we can't have any more. So that brings us to wind power. Wind power has been growing rapidly. There's been enormous investment in it. It's a well-developed source. One of the nice features is illustrated in this picture. You can use land for wind and something else. This is a picture of cows in Germany. They're happily grazing below these pictures of the wind turbines. So if we say we're using some fraction of the United States for wind turbines, you can also still grow soybeans or cattle or something else. The amount of land actually used is only the part at the base of the tower, which is very small. So wind power is very compatible with agriculture, which is important. So how does a wind turbine work? Basically, wind in this diagram is blowing into the page. It then pushes on the wind turbine and makes it go round. It's exactly the same thing as children's pinwheels. So if you have a bigger pinwheel, how much more energy do you get? Well, it goes as the area that the rotor occupies, because that's how many air molecules you have. So as the wind blows by, it delivers energy. The bigger the area, the bigger the energy. So a circle has an area that's proportional to the radius squared. So if you double the size, you get 4 times the power. So this is why you want to make a big wind turbine. And higher wind speed is also important. The power you generate goes as the cube of the wind speed. So even if you have a time where there isn't often a lot of wind, you still can have a peak power coming there because the power it generates is so much bigger. So this red curve is the probability distribution for the wind, and it peaks at around 6 miles an hour. But the power peaks around 12 because even though 12 miles an hour is rarer, it generates so much more power that you end up winning. So this is a graph of wind speed in the United States, and purple is good, and you can see the entire center of the United States is this beautiful big purple band. If we fill it with wind turbines, we are good to go. Problem with wind is that it's seasonal. That, let's go fly a kite. You want to do that usually in the spring in most places. So in the summer, there's very little wind. So if you have enough wind in the big wind season of spring, you may not have enough in summer. And that's a challenge of renewables. Not only is it windier some days than others, there are seasonal factors. But fortunately in the US, there's some distribution, and it's possible to spread much more than it is in Europe. So this is a map of wind power capacity, and you can see that we're pretty smart. We put the wind turbines where the wind is, and that we are doing pretty well. So to generate wind power, the lessons are siting is crucial. You want to build in a windy location. Because of that cube of the wind speed, if you go to a place with double the wind, so if you go from 5 miles an hour to 10 miles an hour, you get 8 times the power. So you want to put big wind farms in windy places. You want to have large rotors to capture lots of wind, and you want to go on a high tower because wind speed increases with height. If you're stretched out on the beach on a nice lazy day and it's all nice and warm, and then you get up to go and get a snack and suddenly it's much colder because it's windier, that's an example where you feel the wind speed increasing with height. So the lesson is you want to build big rotors on high towers in windy locations. But you don't need a lot. 15% of the US land area is enough. And you say 15%, but remember it can coexist with agriculture. You aren't losing that land. You're sharing it with something else. So wind power can absolutely work. Solar power is another option. Slogan people have is 1365. So what is it? It's not an address. It's sounds like a bar in Boston, actually, but it's not. What it is in this case is the amount of power that the sun delivers if you are in a satellite facing the sun 24 hours a day. That's the number of watts that the sun delivers per meter squared. Unfortunately, that's not what you get on Earth for a number of reasons. And the first one is that the Earth turns. So of course, when it's night, solar power is 0. So that 1365 that you get if you have a satellite facing the sun is not what you get on Earth as it's turning. So you lose roughly a factor of 2 due to that. And then there's another factor of 2 due to angle. So you need to divide by 4. If you're not at the equator, the sun's rays don't come in perpendicular, so you actually want to tilt your solar array. But we're really lucky in Boston. A house roof is almost the perfect angle. So if you put a solar panel on your roof, you are absolutely golden. So this is a map of solar power in the US. Red is good, green is less good, but still not bad. There's about a factor of 2 variation. So you do better on solar power in Arizona than you do in Boston or Seattle, but it's not a huge difference the way it is with wind power. So for solar power, it makes sense for it to be local. So the idea for solar power is you want to put solar panels on roofs, roads, deserts. Well, why not put them in all those places we were putting wind power? The answer is that solar power eats all the sunlight. So it's not compatible with agriculture. Unless you're growing mushrooms, you can't coexist with solar power. So solar power constraints are different. On the other hand, what are you using the light on your roof for anyway? It's making your attic hot. So a big advantage to putting those solar panels in is that you are protecting the roof from overheating on hot days, and you're deriving a lot of energy. Similarly, roads, deserts are places where the sunlight isn't used for something else anyway. So it's advantageous for solar power to go local, to put one on your roof. And it turns out 1% of the US land area would be enough. And remember, these are the figures for 100% of the energy used in the US. And you don't actually need anything like that. For one thing, you would share between solar, wind, and other sources. For another, that 100% includes that 60-some% you wasted from burning. You don't need to generate that wasted energy either. And so that's another win that I haven't included so far, which is going to be important later. So if you just put solar panels on suburban roofs, you can supply about 30% of the US electricity, which is roughly equivalent to everything used by residences. So suburban roofs could power the electricity for residences as it's used now. Another option is geothermal power. Geothermal power, again, is site-specific. It comes in two different flavors. One is trying to generate power from very warm areas, and there's some areas in the US that are suitable for that. But a second use of geothermal power is more subtle, and that's to provide a little difference in temperature, and that's suitable everywhere. Portland, Maine, for example, has an airport which uses geothermal power to provide some heating. So if you aren't trying to generate electricity, there's a lot you can do with geothermal power. So that's another renewable. It's one that doesn't come from the sun, so it follows slightly different rules than the others. So one way to think about energy use is to look at what people do. And a fabulous feature that we have now is a tremendous amount of opportunity that's posted on the web. Many, many countries post their energy information in some form. Denmark posts the power it generates all the time. Germany also has a beautiful website showing the power it generates. In the US, California offers these graphs every day of how the state of California generates energy. And you can see it varies from season to season. Obviously, there's more sunlight in the summer than the winter because we're at a higher latitude. In Germany, this is an even more dramatic effect because they're even more north on average than we are. And the amount of sunlight that's generated becomes really impressive. There was a sunny day in Germany last year where solar power in a 24-hour period generated more electricity than all of the other energy sources combined. So solar provided more energy than coal burning, oil burning, nuclear combined. And that's a major industrial country. Even more impressive, in Denmark last year, Denmark's wind power generated more than 100% of all of the electricity used by the country of Denmark. They went over 100%. So renewables aren't just a niche. There are a lot of places where it's already quite large. And there are several US states, including Iowa, where the power generated by renewables exceeds 30%. So generating large fractions is very possible and is increasing constantly. So if you look at these graphs, the first graph is the total power use, and the big black is burning, and that's the part that I would like to get rid of. The part up here is cheating. That's power that California imported from somewhere else, so they aren't responsible for it. And then the renewables are this section down here. So here's a blow up of the renewables. Orange is solar, and so you can see that there's no solar in the dark. Then the sun rises, it peaks around noon, and you get energy that peaks during the day. It was about 6 gigawatts on this day. The blue is hydro. It is spaced out through the day. It's not that they can't turn the dams on and off, but they're balancing the changes in the solar with the hydro. And wind wasn't doing very much on this particular day, so the average renewable power is shown in this graph. In contrast, on this summer day, this was June 19th, the total power use is still pretty similar. They burned a little less and imported a little bit more, but the total power numbers are the same. On the other hand, there's much, much more power generated by the renewables now. So one of the big contributions is wind. Wind was barely visible over here, and it's now a very substantial fraction. And that's partly seasonal in California, and it's partly the day that I happen to pick. So it's very useful to look at one of these if you're trying to understand what our potential for renewable energy is. And California offers them, Germany offers them. It gives you an idea of how people trade off energy fluctuations. The wind's blowing more, the wind's blowing less, the sun's shining more, the sun's shining less. That's one of the biggest challenges in renewable, but one can cleverly mix things. And in Germany, it happens that they are beautifully balanced. So in the winter, it's much windier, so they generate a lot of renewables from the wind. In the summer, they have those very long sunny days, and they almost beautifully cancel. If you look at the total electricity over 12 months, it's almost even because the increase in sunlight in the summer compensates for the lack of wind. Whereas in California, they're somewhat correlated. So I've talked a lot about sources now, but sources aren't the only way that electricity can change our lives. The idea is to change from the way we do things now. So right now we generate electricity by burning fuel, and it suffers from that Carnot efficiency I mentioned. The efficiency fundamentally depends on the temperature difference between the burning furnace and the outside. And you can only make the furnace so hot or it's going to start to melt the metal and be destroyed. So there isn't a lot you can do. The number's roughly 50%. On bad days, it can go up to 60. New gas plants that do multiple uses of the energy can go up to 60% efficiency, but not a lot better. Whereas renewables are not much more efficient. The wind power limit is roughly similar, but not using all the wind is okay. If the wind goes through and the wind turbine doesn't take some of it, it's left over for the next wind turbine, it's left over for your kites, it's not a problem. Similarly, the solar energy that you don't use in your solar power, you can use to heat solar water, it reflects off. There aren't any bad consequences. Whereas the energy that you use to burn, all the carbon emission associated with it, the pollution associated with it, means that energy loss is not only costing you the money to get it out, but then it is all this emission you never use. So by switching from fossil fuel burning plants to renewables, you have these tremendous gains, even though the efficiency itself isn't necessarily better. What happens to the inefficient energy is much better. And cars offer an even bigger opportunity. You thought 60% energy use was bad. Look at cars. In city driving, 84% of the energy you buy in gasoline is wasted. Simply wasted. Even on the highway, it's 74%. Hybrid cars are better. They're about 67% loss, but that's still 2/3 of the power. That's terrible. Electric cars are much better. Their losses are only about 40%. So fruits of this electric revolution can come by making a switch to all electric cars. So the numbers we had from before for gasoline cars, 16% in the city, 26% on the highway. Electric cars are 59 to 62%. That's a huge advantage. Some people like to express these things in miles per gallon. Electric cars are described typically as getting 100 to 130 miles per gallon. And that sounds absolutely fabulous, but then you have to figure out where that electricity came from. In this nice Wikimedia picture, you can see the Tesla Roadster in the front and all those windmills in the back, which you hope are actually powering it. If they're not, if you're plugged into a fossil fuel burning plant, then you still have that energy loss at the plant. So you don't actually do much better. If you plug in your electric car to your fossil fuel burning plant, you still have a big energy loss, you still have the carbon emissions, you still have the pollution. So what you really want to do is go to renewable energy. You have 50% less energy you need, which means all those numbers I gave you before for windmills and solar power generating 100% of the energy, you can have the amount of the US that we need. You don't need 1%, you need 0.5% for solar power, for example. And you get rid of all the emissions. So this is a huge advantage of going all electric. And again, there are inefficiencies in renewables, but they don't matter. Letting the wind go free is not a bad thing. So what are other opportunities that we have? This opportunity is already occurring. It's a picture of an LED light bulb. Incandescent light bulbs are terrible. There used to be an object called the Easy Bake Oven. You used to put an incandescent light bulb in there and you could bake cakes, etc. Turns out about 90% of the energy that you have in a light bulb goes to heating. If you've ever had to turn a light bulb, you know, hot. So that's not the way to go. LEDs are a fundamentally different technology which can allow you to be up to 90% efficient. So this is already happening. It is not possible in the US now to buy a 100-watt incandescent light bulb. This revolution will occur, but if you remember that previous graph, even if we eliminated all energy used for lighting, that's about 14% of the electricity in the United States. A second wonderful thing is this object here, and these are heat pumps. And right now, if you have a furnace, and it's a good gas furnace, you can get efficiencies up to 98%. Wow, 98%, I rock. But it turns out that one of these heat exchangers has an efficiency of over 100%. And you may say, she's got problems, over 100%, you can't do that. But the trick of these heat exchangers is they take energy from the outside, which is cold, but not really cold, and they take some of that energy and they bring it in. So what you're paying is the transport cost in moving heat energy outside, inside. And that's how it can be more than 100% efficient. You're taking energy that's on the outside and you're moving it in. So that outside energy was free to you, you just had to pay the transport cost. And it works the same in the other direction. It also works as an air conditioner. So you have a choice of running it either way. It's both a heater and an air conditioner. And you can get these fabulous more than 100% efficiencies. So this is another win of the all-electric system. This picture over here is an example of a thermoelectric cooler. It's another heating and cooling technology that's typically used in refrigerators or coffee mugs. If you have a plug-in coffee mug, it will often use this technology. And the point is it's very different. Another different technology is Stirling engine cryocoolers. Harvard now uses them in their biolabs because they're much, much more efficient. Other options are be smart, and that means use energy in a different way. And I've given 3 examples of that. One is efficient traffic light. So it's not the traffic light itself. The going to LEDs helps a little bit there. It's using computers to look at what the actual traffic patterns are in a city and use the traffic lights to make the traffic move faster. So by using computation power, you can lower the amount of time people sit in traffic fuming, both literally and figuratively. So that's a very nice advantage that's only recently come from computing power. This is a picture of a heating system. It's one of those heat pumps I showed on the previous page, but it has a smart sensor that looks at where people are in the room. And so it can direct the heat just to where you're sitting. So you heat only your portion of the room. You are warm and toasty. You will get all the pets to be with you because they're not stupid and don't want to be cold, and you don't want to heat the rest of the room. So this is an example of directing energy where you use it. And Just Park is an app which you use on your smartphone that tells you where the parking spaces are so you don't have to go around in traffic. So that is reaching the end of my talk. What I've tried to convince you of is that we have a tremendous opportunity that technology is offering us to change the way that we use energy. And this isn't a case where people are being asked to sacrifice, to wear a big fleece inside, to sweat away in the heat. These are opportunities to change our consumption in ways where we are much happier. Nobody wants to sit in traffic. Nobody wants to look for parking places. We have an opportunity to do these things that make everyone better. And if we just stop burning fuel, we can eliminate these deleterious effects that are of a big concern everywhere. In the developing world, health is the biggest concern because people just cannot breathe. And that's very obvious to everyone who lives there. There's a movie that has come out in China called Under the Dome, which talks about the situation in China. The people of China are very aware of that, and China is making a huge investment in this area. In the US, we tend to be more worried about climate change and its resulting instabilities, and renewables offer this tremendous opportunity to lower our carbon footprint. And good things are already happening. For the first time ever in 2014, the world economy grew, but carbon emission generated from energy did not. They began to decouple, offering us a path to a future where we can continue to be comfortable without having a deleterious effect on the planet. So I think that we have tremendous opportunities in many, many different directions. There are no silver bullets. There is no one solution that's going to do everything. But by moving more toward renewables, by switching to electric cars, by switching to electricity-based heating and cooling, by changing to more efficient technologies, by taking advantage of passive opportunities. Those soda bottle lights are fabulous. They bring power in without using any energy at all. And more of these possibilities are emerging all of the time. We have a tremendous opportunity for a future which is more comfortable and better for us and the planet. And I'm very excited to have a chance to have talked to you about it. Thank you.